Guess what I was telling Andy, at 4 o'clock tomorrow, you guys, you two and Federico will present in any order, it doesn't matter, but like starting at 4.
Okay.
Okay.
By the way, is it, are there any requirements, for the presentation?
No.
Because I have Mac and generally I do my presentations in Beamer. And then when I embed like videos or something, it never works on other people's computers.
Okay, what my thought was to bring your computer in here and then you can just present on Teams. Does that work?
Yes.
Yeah.
Very well. But
Okay, yeah. I think that's easier. Is that okay for you too, Andy? Yeah, okay, you can just, okay, yeah, you can just present from, yeah. You can just present right there, sitting down if you want from your
Okay.
computer, yeah. That's easy enough. Okay, we'll start in like 2 minutes. Frankie, can you hear me?
Sorry, did you say Frank or?
Yeah, well, I know you can hear me, yeah.
Oh, okay.
Yeah, okay. I'm gonna check with you next. Frankie's home from school sick today, so he's sitting on the call.
Okay.
Yeah, yeah,
He can hear you.
okay. Okay. All right, so let's go ahead and get started. I guess now topic 4, we'll probably get to both topic 4 and topic 5 today. And then I don't know if we'll finish topic 5. If not, we'll have some time tomorrow. And then topic 6 tomorrow will be mostly, if not almost all, presentations from people in the wind engineering community who are doing research on thunderstorms and tornadoes to kind of give you an idea of the latest ongoing research and how that ties into what we talked about in the first 4 days. For the class side, if you haven't turned in your homework already, please do so. And I'll assign the second and final homework tonight, which we're going to be on really this the topic that we're going to cover today, which is broadly termed risk assessment. Okay, so we'll show a lot of interesting pictures, a lot of interesting images today. And then once we get through sort of this risk assessment part, hopefully we'll get through everything. We'll move on to codification of thunderstorms and tornadoes in wind load codes and standards. Okay, so before I start, any questions from anybody? Any issues with accessing Dropbox? I know there was at least one person who had issues with that. If for some reason you do, let me know. For your homework, just send it to me via email. Works fine if you can't access Dropbox. And also too, I sent the Dropbox links for the 3 sets of slides in the first 3 topics, and so I'll do the same for the 4th topic today, and then 5th topic if we get there. Send the links to those slides as well. All right, so let's talk about risk assessment today. And so if you remember back when we talked on Monday, we showed the wind load chain. We're all sort of familiar with that. At the end of the day, really the goal of that is to come out with a wind load that ends up in building codes and standards. So now we're going to take it to the next step. So what happens if this load wind load on structures causes damage? So we'll talk a little bit about how that relationship works, and we'll talk a little bit about how to model some damage to structures and other infrastructure. Okay, so first we'll talk about what I would say, and maybe sort of in Europe it's not exactly the same because the structures are built differently. But we'll talk about some common wind damages, and we'll focus initially on residential structures. Again, in the US, mostly wood frame. Okay, so this will be sort of US centered. Okay, so common wind damages for residential. Okay, the first is generally cladding damage. So you might see something like roof shingles, siding, which is usually vinyl, okay, that may get damaged. So very sort of cosmetic damage to structures. And I'll show quite a few pictures just kind of explaining this type of damage and then how it progresses. So that's a common damage. And generally what you see for residential is what we'll call progressive damage. So as the loading increases, gets higher and higher, you start to generate damage. You start to then increase the intensity of damage. You'll go from things like cladding. Okay, then you'll talk about like decking, which we'll also talk about today, which should be on the roof. Okay, maybe we have some internal pressure effects. Then we talked a little bit about that yesterday. Okay, then you might have roof loss. We'll move down here. Loss of the walls, and then okay, eventually complete destruction. Okay, and so going back to the EF scale, I'll show the slide here briefly. Shit. Okay, so if we look at this slide for the EF scale, we talked about this particular one maybe yesterday or the day before. There's a number of damage indicators, and then there's a number of degree of damage. So this degree of damage, this DOD, which runs from 1 to 10, really pretty much describes the progressive damage in residential structures. So you have sort of initial damage, you start to lose parts of the roof covering, you then get to sort of uplift of like roof decking. Sometimes this 5 is entire house shifts off foundation. You don't see that quite as much, even though it's on there. And then what you typically see after you start to lose a little bit of the roof deck, you start seeing the actual roof structure removed. This is like roof trusses, for example. And those walls are still up. And then you start to see collapse of the walls. That's DOD 7 and 8. 9 is all walls collapse. And then 10 is finally sort of complete destruction of the residence. Okay, so this is generally intended in the EF scale to be a progressive damage scale. So the first degree of damage is sort of the first step, threshold of damage, all the way down to destruction. Now, all the damage indicators don't necessarily work that way because some are like trees and things like that. Okay, so it does describe progressive damage, but not like we're talking about with residences. Okay, so something to keep in mind on the EF scale. On the commercial structure side, okay, so these are generally going to be more like engineered buildings. Okay, so these are mostly steel and concrete frame buildings. Okay, if we look at high-rise buildings, and if you go through the history, there's really not too many instances of, and we're talking about tornadoes here specifically, not too many instances of tornadoes sort of affecting a high-rise building. Okay, it happens in hurricanes quite a bit, as you might imagine, in some of the denser urban regions like Miami and South Florida. Okay, so typically what you'll see in hurricanes are cladding that typically take a lot of damage. So especially in high-rise buildings, things like windows. Okay, there's a ton of glass in those structures. Okay, things like flying debris, which we'll cover a little bit today, okay, tend to get picked up in high winds and they damage the cladding. Okay, for tornadoes specifically, there's only one sort of known deformation of a high-rise building, so the actual structural system in history. And so this was called the Great Plains Bank Building. Okay, this was in Lubbock, Texas. F5, back then, not EF, F5 in 1970. Okay, and so this was really, if you go back to the history, okay, those of you who know about Texas Tech University and their wind engineering program, this event in 1970 was really sort of the birth of that wind engineering program at Texas Tech. So this F5 tornado affected really close to the university, okay, and folks went out, and the engineers from Texas Tech went out and studied the damage, and was really sort of the birth of the wind engineering program. Okay, low-rise commercial buildings. So these would be, again, sort of 1, 2, 3-story steel frame structures or concrete frames. Okay, these typically do well. At least the structural system typically does well in tornadoes, unless impacted by heavy debris. Okay, and you may see that especially in the most intense tornadoes where you have, and we saw in the video yesterday, where you have like cars flying around, okay, really heavy debris, okay, that can impact the actual structural systems of these things. And what allows it to do that, and I don't think, I may or may not have a picture, but the cladding, okay, typically takes a big hit in low-rise engineering buildings as well. Usually it's like aluminum or some sort of metal siding, and again, the envelope gets breached and the cladding tends to like peel off a lot of times in tornadoes. Okay, another big issue in low-rise buildings are what I'll call, and I'll have a slide to describe this, so a warehouse-like building. And we'll call this WLB for short. Okay, these particular buildings, due to the way they're constructed, okay, can be subject to catastrophic collapse. Okay, and so these are usually built with what's called a diaphragm system, okay, which just means this. So if you have this structure, okay, assume, again, here's our structure. Okay, this is the wall system here. It's really connected to the roof, usually via some sort of steel truss. Okay, and then at some point down here, there's a column, okay, that's going to support the vertical load. So how the load sort of transfer system works here is if you have a high wind, okay, this load gets, the wall takes the initial impact, the load is transferred from the wall to the truss, okay, and then usually back down into the column. Okay, a problem with that is a lot of these warehouse buildings, and I'll show some pictures of a few, okay, tend to have large openings or potential for large openings. So they may have like a large door where they can rapidly open and close it to let things like shipments or cargo or something in. Okay, so what happens is if you get this opening, okay, again, you get internal pressure built up in here. Okay, you also have your aerodynamic loads externally flow over the roof. Okay, like this. And so the end result then, a lot of times in these systems, is that you sort of break your connection from the roof to the wall. So you basically lose the connection here. Okay, and then you essentially have what amounts to a freestanding wall here. Okay, and then you end up with collapse. Okay, so there's really nothing holding it there. And honestly, we've seen some damages in the US where there's really, the wall isn't even anchored into the ground at all. It's just sort of sitting there. And I'll show some examples of that. So they call that sort of tilt-up construction. If you've ever seen sort of construction of warehouse buildings before they add the roof system, and I have a picture of it, you'll see them basically brace the walls. They'll kind of tilt the walls up, and then they'll brace them with some sort of temporary bracing until the roof can be constructed. Okay, so the roof is really the key piece here that sort of holds everything together. Once that connection is broken, okay, you'll get wall collapse. Okay, and so this sort of collapse is fairly common, at least in the US. And it caused quite a few fatalities over the years where people were sort of in these structures when these walls collapse. Okay, so I'll show some pictures of this. So basically we're going to go through and we'll show some typical wind damages, what you'll see. Most of these are from tornadoes. Okay. Some of the more cosmetic damage you tend to see sometimes in hurricanes as well. Okay, so we'll kind of go through the progressive damage state. So these are mostly pictures that we've taken after damage surveys. Okay, so here's kind of an example. This is after a tornado in Illinois. So you can see a couple things here. One is that you have maybe some minor roof shingle damage. So these are typically like asphalt shingles that are sort of adhered onto the roof deck. You can see some shingle damage here. Okay, you can also see this is kind of covered up now, but you can see damage there. You also see, okay, which is common, you see here, so this is a garage door, and you see this is sort of buckled inward, either from debris or from the wind. Okay, so we also talked about this with internal pressure. Okay, so, and I think I have a good example, I have a couple good examples of this, but think about from an internal pressure standpoint, if air can get inside, the wind can get inside. Okay, you have, again, that sort of upward force on the inside of your roof. You also have maybe uplift on the roof. And so this area here, immediately above the garage door, can tend to be an area where you see enhanced damage. Okay, here's another example. So again, this is a garage door that's been sort of bent inward. And again, you can get pressure in there. Okay, here's another example. This was actually in the derecho in Iowa in 2020. Okay, so this was non-tornadic winds. Okay, here we can see where, and this was and it's a really interesting case study that we won't cover, but you can see here, basically this is the garage. We can never determine if the door was open or bent or anything else. The homeowner wasn't there. You can see what's left of the door right there. And so here you see sort of basically collapse of the portion of the structure that was immediately above the garage. So we suspect that that played a role in the damage level at this particular house, but we can't confirm that. And pretty much everywhere else in this area, there was sort of minor. You can see some minor roof damage here, and then there's sort of just minor roof damage a lot. So in the U.S., typically after these wind events, you'll see them they'll cover the damage with like these plastic or vinyl tarps. So they'll put them over the top of the building to protect it from water ingress and things like that. Okay, now we're starting to move a little bit further down damage progression here. You can see that part of the roof is missing. Okay, so we have roof loss. You can see sort of what's left of the roof deck here. This might have been some sort of asphalt shingle here. The actual roof structure is missing. Okay, and here you can see here that entire roof structure is missing at this location as well. It looks like there may have been a garage right here. Okay, here's another image of damage. Now this was a 2-story wood frame apartment complex, and here you can see basically that the top floor has been almost completely removed from the wind. This was also from Iowa derecho in 2020. So you can see fairly significant damage to this structure. Okay, again, the roof is nowhere to be found. Okay, some interior walls remain on the second floor. Okay, shown another example. This was a tornado in Illinois. Again, you see some roof structure loss there. This one was in, I don't remember where this one was, Tennessee maybe. You can see significant roof damage, a lot of debris as well. You can see there in the foreground. Okay, and we'll also talk about debris here later in the class. Okay, another example. This one is definitely Tennessee in the U.S. So this is basically in the southern U.S. Okay, you can see a lot of different things going on here, talking about progressive damage. Okay, you see windows, doors missing. Okay, so you have this sort of cladding damage. You can see this vinyl siding here that's been ripped off. Okay, you start to see this are just like pressed wood planks. That's the roof deck here. Here's the actual roof structure. Okay, these are trusses. Okay, so you can see a lot of damage here to this particular structure. Okay, another example, okay, kind of the same story here. This was also in Illinois. Okay. Here again, this is another tornado in Illinois. So this was in the Chicago area, and this was a drone. So we had sort of advanced we'd take drones up a lot of times to kind of take a look at damage from an aerial sense where you can really sort of tell a lot more about what's going on. And so here you can see two different, I think they were like apartments or something. Again, entire roof missing here. You can see down into the second floor. Okay, and here also have some roof damage right here. It's gone, and then you can see this sort of exterior wall that's been pushed inward. Okay, I'm kind of going a little backwards here. This shows kind of maybe typical roof damage. You can see how sort of strange that looks. So this was a tornado actually in Champaign, a weak tornado. Okay, you can see some of the roof deck remaining, all the sort of here the decking and the cladding is gone. So all you see is sort of the roof structure left over. But you can also see, and I don't know, it could either speak to construction quality, it could either speak to the flow characteristics of the tornado. Okay, what you don't see is a whole lot of other damage, right? You see this tree, it looks fine. Okay, all these trees look fine, no leaves stripped off, no nothing, right? If that wasn't there, you may not be able to tell anything had actually happened. Okay, similar damage here. Okay, here we're getting into a little higher end damage. So this was also in Illinois. Okay, you can see this house actually, this was the foundation. Okay, the house is pushed off the foundation. Also, okay, the roof structure is gone, and really all that's left is sort of the interior walls of the structure. Okay, and then you have sort of the last state. So this was also in Illinois, and again, I don't know if this speaks to the resistance of the structure to the load, or the sort of the variable load in the tornado itself. But you can see here basically complete destruction of this particular house. Okay, these are left standing. Okay, this one is just basically a pile of debris sort of just off the initial foundation of the structure, which is right here. Okay, so this is fairly common. And again, if you kind of go through the EF scale and look, the highest DOD is what they call slab, which is just sort of the foundation swept clean. Here, most of the debris is sort of laying in the structure. So yeah, so people were injured here at this house. I think they ended up surviving, but still pretty scary when you go out and look at it. Yeah, you see this damage quite a bit in tornadoes, and this one was a rated EF3 maybe, EF2, so not even on the high, really on the high end. But again, kind of show you that progressive damage state in residential. Okay, here's what you might typically see for high-rise buildings. These pictures are both in hurricanes. So this is one's in Texas and one's in Louisiana. So on the Gulf of Mexico coast in the US. And what you see is just a ton of window damage, cladding damage from debris, and sometimes both from wind pressure itself and from flying debris. A lot of windows then get knocked out. Okay, here's the building in Lubbock. Okay, it's still operational now. It has a permanent deformation. I can't remember how much now, a few inches, I think. Okay, so this is still operational, but this was the high-rise building that was permanently deformed in a tornado. So in general, and I know you guys probably as engineers, you might, be aware of these things like performance-based design of structures. That's sort of a new topic, or not necessarily new, but an up and coming topic. And so usually for windstorms, it's not as much sort of making sure the structure doesn't deform, or, like an earthquake, you're worried about excessive deformation, things like that. Wind, not as much. Usually it's the envelope of the structure, the cladding are things that are typically damaged in these storms. Oh yeah, I do have a picture. Okay, so here's an example of sort of a low-rise steel frame building. And so sort of the steel structure here is pretty much intact. It's really all the cladding that got ripped off. So this thing is really kind of down to its skeleton. This was in a tornado in Missouri. Okay, so you can see the envelope damage is significant, but the actual structure itself fared okay. But of course, it doesn't really matter because, that poses a serious threat to anybody inside the building. And certainly you're going to have to probably tear that down and rebuild. So it doesn't necessarily matter if the structure survives or not. Here's another example. So this was also in that same tornado. So this was an EF5 tornado in Missouri. So this one struck a hospital. And so this is a whole interesting case study in and of itself. This was that the building circled is a steel frame, 7-story steel frame, and then a concrete frame, 9-story there immediately to the left, had a lot of cladding damage. And in fact, so much, the structure was fine. But it had so much cladding damage, and obviously it was a hospital, so there's a lot of like hazardous materials and things in there. And so basically they had to tear this hospital down. So it doesn't necessarily, again, matter if the structure survives. And that's a whole different discussion around performance-based design and structure functionality and other things that are related to wind, but not wind specific. The last thing here I'll show on the pictures are these warehouse-like buildings. And you probably hear, especially out in the suburbs and things like that, like department stores or, large stores maybe sort of have this type of construction where it's sort of a large standalone building. It has a very large footprint. It also has sort of a large continuous internal volume. So basically just one giant internal volume inside, not a lot of partitions for like a store, or they need to like get, again, sort of like it's a distribution facility or something. They're bringing a lot of goods in and shipping them out. So it's just a big open space inside. Tilt up walls, which I mentioned, I'm pretty sure I have a picture of that. They also have these large roll up doors or docks for delivery. So you might have seen like truck docks on these structures where a tractor trailer can back into this dock and deliver the goods. Okay, and it also can include, at least in the US, things like these big box stores, which are like Walmart, which are just sort of giant warehouse-like stores, but also things like data centers, which are becoming more and more important now, typically have this type of construction. They're sort of large buildings with, obviously there's not a lot of people in them. So historically for design of structures, those don't get rated as high importance. But now they probably are quite a bit more important since these sort of data centers are popping up everywhere. Okay, so here's an example too. So here are a couple examples of tilt-up collapses. So here, this was in Missouri after a tornado. These are large concrete panels, tilt-up panels, which you can see under construction here. Okay, so you can see they're very large, very heavy concrete panels. Before the roof goes in and they get connected together, they're tilted up and sort of these temporary braces are put in to hold the walls up until the roof gets connected. So that could give you an idea of the stability of those walls if there's nothing holding them together. You also see similar construction in like gymnasiums. So this is a gym here. You can see this, again, gym has to be a large open space by design. And so you have this, basically this wall collapse here. These, you can see the metal roof trusses here. Okay, there's the couple trusses are actually collapsed. Okay, and so the same thing happens in these cases. And here's a couple more examples. This is just from 2024 in the US. So there are more than this. A lot of these warehouse-like buildings collapse or partial collapse after tornadoes. And I showed this one the other day. This was in an Amazon warehouse facility in Illinois. Okay, this was after a tornado in Florida, Michigan, and Oklahoma. So you can see these tilt-up panels that are just laying on the ground after collapse. Okay, so one of the things for the tornado loading code, which hopefully we'll get to today, that we'll talk about, is to maybe give these particular structures a little more importance and to increase sort of the design loads for these particular structures because they are so susceptible to collapse and sort of a life safety issue. So we did a detailed study of this structure here, which was in Michigan, which is in sort of the Midwest, so fairly close to Illinois. And found that there were like 70 people inside the building at the time of the tornado. This was a distribution facility. Fortunately, they were all in this section here as the tornado came through. But again, it may pose a significant sort of life safety risk to people being in these buildings. Yeah, and so this is just another picture of another collapse. This is a Walmart in the U.S. The same tornado that did the damage here to this big box store also did damage here in Missouri. So a lot of damage, typical damage that you would see in tornadoes, especially. Yeah, all the way from basically the beginnings of damage all the way till complete collapse. Okay, any questions on that? Okay.
You showed a photo, I think it was 515.
Mhm.
The building got crushed in the residential building.
Here.
Yeah, and this building, neighboring buildings, nothing. How come?
Yeah, that's a good question. So let me grab my water here too. So the debate has always sort of gone like this, where the structural engineers say, yes, it's sort of poor construction's responsible, and the meteorologists would probably say, no, it's probably just the variability in the tornado itself, right? So, and we've shown some of the videos in class of where the tornado's doing crazy things, right? These small subvortices pop up out of nowhere and do damage, and so it's an open question. I mean, we did on this particular building, because it is so interesting, did sort of an LES study where we tried to replicate the neighborhood as basically obstacles, and then ran a similar tornado through. And what we did find was that there was sort of this acceleration in wind speed in that general area. Okay, so it doesn't prove it, but it was interesting that we sort of noticed it in around the same spot as we saw this damage. So good question. We didn't, I mean, you can go in and you can look and see how this thing generally was connected, right? So the biggest thing in these damages is how the structure is connected to itself. So how well is the roof connected to the wall? How well is the wall connected to the foundation? And you can find weak links in those, but they may be in the other houses too. You just can't go in and see it. So it's a good question. It's really sort of open right now. Right. And a lot of times what we have done, and unfortunately this family was injured, but we will go out and we usually have a social scientist with us, and they'll ask the homeowner specific questions. And we'll be with them and try to understand a little bit more about, some of it is kind of how they responded to the tornado coming, but also things like, was the garage door open? Have you had any, or what happened first? Did the windows blow out, or did the roof come off, or something like that, right? Because at this final state, there's not a whole lot you can tell. So yeah, really good question. We don't really know. Yeah, I think that's the answer, and mostly just because of all the uncertainties there. And we'll talk about that actually today in the damage modeling. Good question. Any other questions? Yes, sir.
You said areas study on the same area. So you were modeling the neighborhood scale, kind of like tornado keeping propagating through this domain.
Yes.
How do you estimate like the inflow height in reality? Do you have some estimation of what would be the height of the inflow and it goes down with the center?
Yeah, no, you can't estimate it, I guess. And so the tornado the tornado is the least realistic thing about the simulation. Because we don't even know the structure, right? We talked a little bit about this yesterday. We assumed that it was for this one, I think we assumed single cell vortex, but we don't even know the dimension. We don't even know the dimension relative to the building and things like that. So we were really estimating on the tornado characteristics and things like inflow depth and things like that. We don't understand. So basically the LES, and I think this one had, yeah, so things like debris, zero feedback there. So not accounted for. We basically said if the wind speed got high enough, we basically removed a piece of the structure, like the roof would be removed or something like that. So we can, but there's no sort of two-way feedback there. So there's no way to really estimate it. The model we use is sort of the same one that the lead modeler had used for a while. So just sort of like a rectangular domain. There's no thunderstorm or anything. You sort of, swirling inflow and an updraft at the upper boundary, which like, tornado like vortex. So yeah, good question. I think that's what at least us and others are trying to sort of drive towards more realistic simulations. Like how can we characterize a tornado better to be able to then implement that in a LES, for example. And so we'll talk about that today too. How are you going to do that from this end result? What does that tell you about the tornado? Okay. So you guys will do that yourselves in the homework, some of you. And so, yeah, so this leads me right into the next point I was going to make, which is, okay, how do we find stuff out about the tornado, right? And so all these pictures that I've shown have been done almost entirely by us going out on damage surveys. Okay, and so what can we do from a damage survey? Well, it turns out a lot. And since we don't have a lot of measurements of tornadoes or none, this is really the only way that we can try to understand what happened. Okay, so from damage surveys, we can do a couple different things. So one, we can get information on the wind environment. Okay, and I have a set of slides. Okay, what we'll talk about is how to do some different wind speed estimation techniques. Okay, we already talked about a simple one, which was the EF scale, right, where the wind speed is based on damage, but we'll also talk about some other wind speed estimation techniques. Okay, from the damage survey and also from potentially information on the damage itself, or from the wind environment and also potentially from information from the damage itself. Okay, we can understand something about the wind-induced loading, which we talked about yesterday. Okay, obviously we can get information on the different levels of damage from a damage survey, and this could be for buildings, it could be for anything. Okay, we'll talk about an example of tree damage, okay, and how that can give you some information about the wind environment. And then also, obviously, you can get information on debris, okay, which is significant. Historically, wind engineers, especially for wind loading, design wind loading, has sort of neglected the effects of debris, although we know, especially in tornadoes, that debris is significant. So you can go any of these ways. Okay, also here, okay, if you get information on the wind environment, okay, you can then sort of translate it information to model information on these three. Okay, so wind environment is always sort of the first step. You get the wind speed, you get the wind direction. For your homework, you did the Rankine vortex model. You have a speed and a direction. Okay, then you can have your structure of interest, and then you could essentially transform that speed and direction time history into wind loading, right? Based on obviously the wind velocity and then the angle of attack on your building. Okay, so I wanted to kind of step you through a typical post-storm assessment or damage survey, okay, for lack of a better word. Okay, so this is, we don't have to go through this. So basically, again, this is kind of what I talked about, really sort of the first couple things. We'll talk about fragilities today a little bit too. Okay, if you do a ground survey, okay, you get a wind speed estimate, and then you can relate that to the level of damage that you observe. Okay. And your damage level can be something like this, right? We talked about the EF scale. This is a damage level. You have a certain degree of damage that you go out into the field and you assess. So here's an example from a tornado. You go out and do the survey, you go and look at the damage to the structure, and you say, okay, it's DOD 4, uplift of roof deck and loss of significant roof covering material, collapse of chimney. Okay, so for example, I think this is what's left of the chimney there. Okay, so you could go out and you would go through this list of DODs and you would say, okay, it's DOD 4, for example. Okay, and you would assign a wind speed to that. Okay, here's another example. I showed this picture before. You would go out and rate the DOD for this one. You could say, okay, it's DOD 6, okay, and give that a wind speed. I showed this image before. Okay, so this was also in Illinois. You say, okay, this one's pretty significant. This is DOD 8. Most of the walls collapsed except small interior rooms. Okay, it seems to fit the end damage state there fairly well. Oops. Okay, some other things that you might find out. So a lot of times too, especially in the southern US that have these really sort of tall, slender trees, you may have difficulty distinguishing what's causing, if it's the wind causing damage or it's falling trees. Okay, so here's a couple different examples where there's very little wind damage. Remember, we sort of look for shingle damage or sort of cladding damage first on the roof. Here, basically, the tree split the structure in half. You can kind of see what's left of the structure there as a tree fell right on top of it. Here you can see another example of that. And then here is an example of wind damage. So when you go out on these damage surveys, it does require you to be a little bit of a forensic engineer to go out and try to determine, okay, what actually caused the damage that I'm observing. Okay, another thing that we'll do, and you guys will do a homework on this, is looking at tree damage. And so a lot of times after tornadoes, there'll be a lot of tree damage. Okay, sometimes, and maybe I think Dave Sills from Western Ontario will talk about it tomorrow, some of the work that they're doing with tree damage in forests. So what you'll see, and we'll show quite a more images of this, is there'll be a lot of trees and they'll fall in a specific direction. Okay, and so one thing is that we'll go out there and we'll look at fallen trees and we'll sort of record the direction that the tree fell. Okay, in a single tree in isolation, it doesn't mean a whole lot. Okay, when you have hundreds of trees that all fall in sort of different directions in a very coherent pattern, okay, then you can start to do true wind speed estimation based on those, and we'll talk more about that. Okay, another thing that we've done a lot of is what we call wind indicators. So things like traffic signs, okay, that end up failing after these wind events. Here's an example from Australia that we did not do, but so basically just use, simple engineering principles, the surface area of the sign, okay, sort of the resistance of the material, the steel or aluminum or whatever sort of material it is, the modulus of elasticity and the yield stress, and you can estimate what is the wind speed that would cause that structure to fail. We might have another picture of that. So here's an example in a tornado. Okay, and just a simple process for estimating the wind speed. So you can either sort of estimate the material properties, or we've also taken them into the structures lab and done actual testing to see, for example, what the plastic moment is, what the nominal moment is of these steel posts. And so here you can see an example in the US. Okay, another thing that you could do is potentially track debris. Okay, and so you can then sort of potentially incorporate these things into debris flight models. So here's an example from Georgia, maybe, where this debris was all sort of pink in color. There was a house that had sort of a pink paint on it, and so you can basically win and find these different pieces of debris. You know the start point roughly, you know the end point, and then you can do some either estimate tornado wind fields based on the location of the debris, and you can do some debris flight modeling as well. So also kind of included an example. So what typically we would go out and do for a damage survey. This was in Kentucky, I believe, in 2021. So this was a fairly significant tornado outbreak in the US. So we had a couple different objectives. So one being, can we verify that it is a violent tornado? So basically stronger than like 80 meter per second winds. And so doing some of this wind indicator analysis, tree fall or whatever to verify that. The second thing that we're looking at, and something we're looking at right now, is looking at how does the tornado and the building interact with each other, especially large buildings. And so we're looking for that. Also looking for what Josip mentioned earlier, what we're calling outlier structures that either behaved a lot better than we expect or worse than we expect. What can we learn about those structures? Like the one that you saw that was collapsed, the other structures next to it had some damage, but were overall okay. And then the fourth one is then just going through a traditional DoD assessment where you go in, you look at the structure, and you give it a degree of damage from the EF scale. Okay, so again, you sort of go out and do all these things. You take the drone, you take your ground-based photos, you take measurements of things. Okay, all trying to get this information that I mentioned: the wind environment, loading, damage, and debris. Okay, we'll talk more about tree fall specifically. Okay, so a lot of times after these events, there are aerial imagery that's left behind. You can use GIS or some other geographic software to draw the patterns of tree fall. And it may be a little bit harder to see here. See if we can zoom in. Okay, so those arrows basically point the direction that the tree fell. Okay, and so you can see a lot of times they have very sort of coherent patterns when you looked at them in space. And so what you can do, let's say that the tornado is moving in this direction. Okay, you can take a transect of trees sort of perpendicular to that. Okay, you can get some sort of average direction or instantaneous or average direction of trees along this transect, for example. And then what you can do is compare that to your Rankine vortex model, for example. So the orange arrows here are the sort of the average observed pattern of tree fall. And then the blue is from a simulation. So similar to what you did in your homework. So add a wrinkle to that for your second homework. So you can see basically then you can sort of have some sort of best match pattern based on, try to minimize the difference in the angles between each of these locations. Okay, and then you can estimate a wind field from this. Okay, so you basically run these patterns, and I'll show more about this later. Okay, maybe some other more crazy damage after. So this was at the same tornado. You can see the tree fall here. Okay, all sort of in this direction, at least from here, you can kind of see it laying down. But okay, the key thing is here you have these train cars that are overturned. Okay, so obviously they were sitting on the tracks. You can see a couple that had been thrown from, assuming these were all sort of sitting connected at some point. Okay, the tornado came through. Okay, and you can see that it's been tipped over. Some of the cars have been thrown. So you can use other wind speed estimation techniques to estimate what sort of wind speeds it would take to do this type of damage. Okay. So any questions on just general damage surveys? Okay, so what we'll talk about now are some wind speed estimation techniques that are typically used. And certainly even for, certainly not only the EF scale, but the international Fujita scale, which is used in Europe, okay, we maybe using one or more of these techniques either now or at some point in the near future. Okay, so these are any sort of damage survey. If you guys are interested in damage, I would certainly encourage you to go out and look at these things, okay, and potentially use some of these techniques to estimate the damage. Okay, so we'll start with the basic one. We don't have to go into depth here because we talked about this already. So the first one is the obvious one. That's the EF scale. If you look at the history, Fujita started this scale starting going back in the 70s. Okay, this was updated to the EF scale in around 2007. Okay, so these are sort of EF scale is just an extension of the F scale. The EF scale added things like degrees of damage, added things like damage indicators. Okay, so it's easier in theory to go out and rate a tornado. So in the US, the meteorologist at there's the National Weather Service, which is the government weather service. Okay, they have all these offices throughout the US. If a tornado happens in their area, they're the ones responsible for going out and doing a damage survey and giving the tornado a rating. Okay, so each tornado that occurs in theory has to be given a rating, and the local weather service offices go out and do the damage survey. Okay, we won't go through this here, the EF scale. We talked about this. There's a few differences between the E and F scale, namely the wind speeds required to do a specific damage. Okay, and the old F scale, F5 damage was 262 to 317 miles per hour. Okay, they basically said now EF5 damage is greater than 200 miles per hour, 89 meters per second. Okay, so they changed the speeds. They did relate the two to make sure, that the overall tornado climatology doesn't change in the US. But again, it brings the question from an engineering standpoint, what wind speed does it require to do specific damages? Now in the US, these things are undergoing a change in the US to add not only the EF scale as a wind speed estimation technique, but to add other techniques as well. So the weather service, if they go out, for example, they don't necessarily, at some point, will not always have to use the EF scale to rate damage. So we'll talk about a couple different methods to do that. Okay. So we talked about this. So one, the EF scale. So EF scale is going through an update. Okay. One of the big things that will be changed is, okay, we saw this lower bound, upper bound, and expected in the old EF scale. This was LB, EXP, and UB in the EF scale. Now they're changing that to, which was its intention, is typical resistance, weaker than typical resistance, and stronger than typical resistance. So it's really more of a construction quality thing that they're planning on using going forward. So, and this is all sort of in response to concerns with the EF scale. So after there were a lot of big tornadoes, damaging tornadoes in the US about 15 years ago. And it really sort of brought out some concerns that there really weren't enough DIs and DODs in the EF scale. And some of the guidance was confusing on what you needed to do. And so for these tornadoes, there were two particular tornadoes, one in Alabama and one in Missouri, that were both, well, one was rated EF4 and the other one was rated EF5, but really started to show some of the issues with the EF scale, especially when you get to really high wind speeds. There's just not enough information in there for you to make a determination on sort of how intense you think it is. And so you can see this one, which I worked on in the US, was really, there's really not enough DI and DODs to truly sort of characterize the tornado intensity. Okay, but what you'll see too, this is the IF scale here. Okay, the IF scale works the same way. Okay, so basically you have some IF scale that they have sort of intermediate, like 0.5, 1.5, 2.5. Okay, ultimately going back to a, again, from a wind speed to a damage. You can see the IF5, which is 130 meters per second, which is quite a bit higher than the US one. And I think, Andy, you were part of that, or yeah.
Yeah, like this.
What's that?
Yeah, like this.
Okay. So good. You guys tell me more about how that's going. Yeah. So and then are there sort of any additional changes planned for that at some point? No. Okay. And this was fairly recent, right? The change, the sort of the updated scale. 2026. Okay. Okay. So yeah, so this one was this recently updated IF scale, right? And the EF scale has not been updated, but it should be within the next 2 years, I would say, where there'll be more DIs, more information on DODs. So basically sort of a more comprehensive assessment using damage. We don't have to go too much about this, but I showed some information on aerial imagery and things like that. So that is just much more commonplace nowadays. Things like drones, a lot of people have them. They're easy to go up and fly after these events. There's also satellite imagery, fixed wing imagery. There's all sorts of different aerial imagery available. Some of it is commercially available at like 8 centimeter resolution. So it gives you a better opportunity to study different characteristics of tornadoes. So things like tree fall, like I mentioned, much easier to assess if you have some sort of aerial imagery to kind of see the entire picture instead of going tree to tree on the ground and doing it. Here just kind of shows an example of that, what you can see. So for example, this would be maybe what you see from a ground survey on the top. And then here's what you can see from the aerial survey. So you sort of get another surface to look at, another more information to try to make a determination on damage levels. So remote sensing in the new, so it's not necessarily a technique, but it's going to be used for these other techniques that I'll talk about. So sort of one technique is just using in situ measurements, things like anemometers. Okay, this doesn't happen as much. Here's a couple examples, and I've sort of showed these. And that looks weird, but things like the pressure drop, things like wind speed. Okay, again, this is sort of be a wind speed estimation technique. So if you have a instrument, an anemometer or something in the path of the tornado, you can use that as an estimation technique, which is just sort of essentially just taking the wind speed and saying this is how strong it was. Now you could do some sort of standardization about that. Let's say you collected this wind speed. This wind speed was collected at 2.5 meter height. Okay, in theory, you probably want to convert that to 10 meter height to be standard, but there's really no great method to do that right now. So there's going to be, eventually there might be a method to convert a speed from 2.5 meters in a tornado to 10 meter. Okay, but we don't know what that conversion actually looks like. Okay, so for now, we assume that whatever's collected at 2.5 meters, that's basically equal to the wind speed at 10 meters. So basically a flat profile, even though that's probably not the case. Another thing that we're going to use, and I don't know why the slides are looking weird, is radar imagery. Okay, so you can look at, again, radar gives you information on sort of particle motion toward and away from the radar. Okay, and so you can use those motions to estimate the wind speeds. And so here just shows an example. And here I think is more a critical point. So this is from some studies maybe 10 years ago or so. Okay, so the sort of the hatched histogram is from the EF scale. And so this is the, for the same set of tornadoes, the EF scale rating. And then these sort of dark, solid color histogram is from estimates from the radar itself. Okay, so you can see sort of a distinct difference there in a damage-based estimate of the wind speed and a radar-based estimate of the wind speed. So there will be a method to estimate wind speeds with radar. And so here's an example, and we use these profiles for ASC 722, which we'll get to today probably. But here's an example. This is from one particular tornado in 2013, maybe. Okay, that shows this is at various time. These are at various times. Okay, looking at the profile, and they had information on the radar as low as 5 meters here. But what you can see is the highest wind speed is closest to the ground. And they normalized this to 10-meter height. Okay, so really interesting results. That's kind of been driving the meteorological side on radar is, yes, the speeds, the highest speeds are very close to the ground. Okay, other methods, we'll talk about tree fall. Okay, so again, this is just a snapshot of what tree fall would look like. We can see within this particular area, the trees generally fall in the same direction. Okay. Another thing that you can do is just simply forensics, which we talked about a little bit with sign damage. Okay, so just do a forensic engineering estimate, right? You know the surface area of the sign. You can get the drag coefficient of the sign. Okay, you have that information, then you can estimate the wind speed, okay, required to knock it down, assuming you know too the resistance properties of the structure itself. Okay, so what there will be, so there'll be this ASCE, another standard that will basically have a list of wind speed estimation techniques. It'll include in situ measurements, it'll include tree fall, forensics, radar. Okay, so it'll have all these different methods that you can use, and there'll be sort of a standard process that you need to follow to be able to use these different methods. Okay, and ultimately, again, for the standards, we need to make sure that we're at standard conditions, 3-second gust, which you're all familiar with, 10 meters above ground, and then open terrain. Now, how you convert those, for the most part, it's anybody's guess. But that's ultimately, at least in the standard, what you need to consider. Okay. So any questions on that? So that, and certainly if you're interested in different wind speed estimation techniques, you can reach out to me. Pretty heavily involved in that standards committee, because a lot of it came out of the work that we did on Joplin way back in 2011.
What's the typical pressure drop?
The good question. There's not enough information to tell. What I will tell you is that this one, which was 100 millibar drop, is, I think, on the extreme end. Yeah. What did we see? I'm not comparing it to tornado, but in dust devils, it was like, what did we see? 3 millibar drop, maybe something like that. So somewhere higher than that, but lower than 100 typically. Yeah. But again, there's just not a lot of measurements on that. But if you're interested, I can get that. There's one paper I know that has a handful of pressure drops in tornadoes. Okay, so let's see. I don't want to kill my, okay. Let me just see if I do this here. Okay. All right, so let's talk about one particular wind speed estimation method. And we're going to talk about tree fall patterns specifically, because it's probably one of the ones that I was more heavily involved with. And talk just generally about how this method will work. Okay, so this background is stuff that we've pretty much covered quite a bit in class. We don't have a lot of full-scale data. Okay, a lot of times radar, although it's good, can't get really close to the ground because the obstacles near the ground tend to reflect the radar beam, and it doesn't generally get good information below 5 meters. That case I just showed was unique. Most is above 20 meters, and a lot above 50 meters. And again, pretty much everything up to this point has been done with the EF scale. And there, again, we'll talk about this today. There's kind of been a push for design for tornadoes in the US, and now it's included in ASC 722. Okay, the key thing is we need to estimate wind speed, and maybe the damage, maybe estimating wind speed from damage is not necessarily the best thing to do all the time. Okay, so one thing we turned to was tree fall analysis. And so this analysis goes way back to over 100 years ago in Europe. Okay, a couple scientists, Letzman and Wegner, basically came up with these illustrations of tree fall patterns for sort of different tornado structures. And you can see Letzman's schematic of different tree fall patterns on the bottom left-hand side there. So on the left side is G max, which we covered a little bit yesterday, which is the ratio of the translation or the rotational speed to the translational speed. And then on top is alpha. And so this is the sort of inflow parameter that I talked about. And so what you see, and in this particular sketch, the tornado is moving from bottom to top. So it's moving in this direction. Okay, and what you can see is that the pattern changes, okay, based on this alpha value, which is the inflow angle, and this G max, which is the ratio of rotation to translation. Okay, so for example, when G max is from 1 to 3.5, okay, basically what you see is the fall direction is in the same direction as translation. Okay. If the rotation gets stronger relative to translation, which is when it gets greater than 3.5, what you see is very near the tornado center, the trees fall backwards towards opposite the direction of translation. Okay, and that's for a 0-degree inflow angle. You see that change as the inflow angle changes as well. Okay, so what you can see, and the key thing here is that the pattern changes based on characteristics of the vortex itself. Okay, and so the method was great. It existed over 100 years ago. The issue was, and it doesn't show up great in this presentation, but we didn't really have things like a ton of aerial photos to be able to apply these methods. Okay, and even if we did, there are a lot of times thousands or millions of trees that may fall after tornadoes, like especially in these forested regions. Okay, let me see if I can zoom in and show something well. So here, for example, oops, oh, maybe I can't do that. Here, see if we can get out of this real quick. Okay, so if you really zoom in here, okay, you can see some of the detail of this pattern. And this is a particularly interesting one because you can just see a swirl in the tree fall, right? So you can see these are basically the tree roots. Here you can see what happens to the trees. Okay, you can sort of draw then, and you can do this with the GIS program. Okay, you can sort of draw the direction that the trees fall. Okay, so they're doing some interesting things here. Okay, so maybe something like this. You can see sort of a swirling pattern here, okay, in the trees themselves. Okay, here's another example. Okay, you can zoom in. And you can kind of tell. So typically you want high resolution imagery to be able to do this. Okay. It's hard to say specifically, but it sort of looks like for this one, it maybe has a pattern like this. Okay. So if you know information on where the tornado is moving, let's see if this one shows up any better. Yeah, forested regions are always hard. This one has some topography too, so that makes it even more challenging. Okay, but basically then you know which way the tornado is moving. Okay, you know information on the tree fall pattern. Okay, you can use this method, okay, to estimate a wind field. Okay, so here's another example. This shows up a little bit better since we kind of annotated these. Okay, so you can see sort of the different patterns in the tree fall, and again, very coherent patterns that you can see. And you can estimate too where the tornado center is and how it moves relative to the tree fall. Here's another example from Alabama. Okay, and so I think the colors represent in general the direction of fall. And so in these, what you can see is, you can kind of tell here, but these patterns sort of look like this on one side of the tornado, and then maybe like this on the other side. Okay, and the tornado is moving in this direction. Okay, so there are a lot of different striking images of tree fall now, especially since aerial imagery is just super common. Okay, so now we can use these methods that were developed 100 years ago. Okay, we can modify them. And then we can develop wind fields. Okay, so let me see this thing. Okay, so here's an example. Right now, there's a couple ways, and Dave Sills may talk about it tomorrow. Initially, and when I started this as a postdoc, I was in manually tagging trees in ArcGIS, like tens of thousands of trees. Going in there, okay, creating a vector, drawing it myself, okay, and saving that information in there. There are some methods now using machine learning, artificial intelligence to try to identify a tree in the image and also give it a direction. Okay, there's still a lot of work to be done there, especially like areas in forests where everything looks the same or similar. And a lot of times, like, let's say a forest in Canada may have a different characteristic than a forest in the US. Okay, if it's trained on one or the other, it may not work well in a different sort of geographic location. Okay, so how do we estimate the wind speed and wind field? Okay, it's basically what we talked about yesterday. The formatting is weird on this, but here again, use Rankine vortex model, okay, to do that. And we talked about this yesterday. Okay, sort of this schematic, and things should look familiar. Okay, so the parameter description is pretty much the same as we talked about yesterday, except now this is important for your homework. We're going to add another parameter in the Rankine model, and it's really sort of an external parameter. It's not necessarily parameterized in the wind field. It's the critical wind speed of tree fall. Okay, so you can use an average speed for all your grid points, which you can basically create as trees. You can use some randomized value, or you can use information from things like tree resistance studies, where they pull down trees and they get some uncertainty in the load it takes to knock them down. Okay, but here in the tree fall, they have all our same parameters. Now we have a critical wind speed of tree fall. So in your wind field model, okay, that you develop like the Rankine model, okay, as soon as your wind speed exceeds the critical speed, the tree falls at the direction of the wind at that time. Okay. And so how that looks, so here's an example. Okay, this could be the same as you do in your homework. Okay, you have just some simple analytical model of your wind field. Okay, you sort of move it through your grid. And so when the wind speed exceeds some critical speed, okay, your tree falls at the direction at that point in time in your model. So the red vector is the wind velocity at a given time. Once it exceeds, I don't know, it might be 35 or 40 meters per second here. Okay, the tree falls given by that direction. And what you can see is that, okay, you come up with a tree fall pattern, right? So this particular pattern, the tornado is moving from left to right. Some of the tree fall is opposite the direction of translation. okay, as you start to move away from the center, okay, those trees start to fall, at least on the right side of the tornado, because this is the way it's translating, start to fall opposite the direction of translation. Okay, and what you can do, again, the homework example I gave you is just a steady state vortex. It's not changing in time. Okay, and so what you see, if the tornado just moves over some area, okay, the fall patterns are going to look the same. Okay, every transect has the same fall pattern in this case. But what you can do is take information, if you wanted to do some comparison to your observation to your model, is you can do things like compare the directions of the fall with the directions in the observation. Okay, a lot of tree fall patterns have some what we're calling convergence line here. So basically the convergence line is when the fall direction is either 180 degrees opposite of the translation or in the same direction as translation. So you can see here, these vectors sort of converge, or you can compare some average direction along the transect. Okay, so if this was an output that the model produced, you can go back and compare it to your observations. Okay, here's just an example. So this is an actual tornado from Missouri. Okay, so this one I tagged pretty much all myself. I don't even remember how many trees there were. But you can zoom in, try to zoom in here and show you some of the different patterns. Okay, so the tornado track, best guess was sort of that red dotted line there. Okay, so you can see that on this side, okay, for example, you have, and again, the tornado is actually changing characteristics here. Okay, you can see on this side, the trees in general falling inward towards the center. Okay, the tornado is moving in this direction. Okay, and you can see here, some of it's out here like this, some fall pattern. Once you get over here, it starts to fall more like this towards the tornado. Okay, here, things are more closer to the direction of translation. Okay, so, and up here, it's something like this, right? So you can see this sort of clear convergent pattern in the tree fall. Okay, and so what you can do is do that. And this is just an example from a particular case in Joplin. Okay, and then here I showed that sort of swirling pattern, and it doesn't show up very well on that, but kind of show you some of the interesting patterns. This is right near the tornado beginning. Tornado just starting here. There's kind of a small gap, and then basically there's consistent tree fall through the entire length. So here shows an example of the entire path of the tornado, just as the tree fall starts, and then there's a sort of a huge swath of time where the tree fall pattern is very similar to one another. And then as you move away, this one's actually pretty close too, although the tornado changes direction. And then the tornado dies off. Okay, and so what you can do, similar, you have your Rankine vortex parameters. Okay, you generate the modeled tree fall, you compare it to the observations. Okay, your best match then is the wind field that you'll use as your estimate. And so here's an example from this particular one in Missouri. Okay, where this is the maximum wind speed and got close to EF5, EF4 here. I think it was like 80 to 85 meters per second was our maximum estimate. And another thing that you could do, and similar to what you did in your homework, was that you can generate a time history at a particular location. Okay, so let's say you went out and you studied, one structure that had a lot of damage compared to the surrounding ones, right? Or vice versa. You can go out and, okay, well, I want to do a wind field model. I develop a wind field time history, wind direction time history, wind speed time history for that location. Okay, and then you can transfer that into loading damage, which we'll talk about next, and things like that. So it gives you the opportunity to generate these things for individual locations in addition to sort of more broadly across a particular location. And a couple other things on tree fall. So when I started at Illinois, and I don't know how aware you guys are with US geography, but there's a lot of agriculture there, things like corn, soybeans. And what I noticed, this was after a tornado in 2016. So I was just here, this is corn. So this was in the fall. And what you can see is a tornado, okay, left very clear patterns in the corn, okay? And I was sort of shocked by how similar some of these patterns look like to trees. And so we did basically this, you can do the same type of analysis with corn or any sort of crop really, and do estimated wind speed. Okay, we also estimated things in soybeans, which was weird, but some really interesting flow patterns observed based on damage to things like crops. But here's just an example of what you can do. So this was this was the same case as this one. Okay, estimated the peak wind speed around 49 meters per second for this particular case. And again, you can develop a wind field. Okay, also saw in some interesting flow patterns in soybeans, which don't really like snap. Like here, the corn is either snapped off or laid. It's just sort of laid down. It didn't come back up. Soybeans are a little weirder, but you see these sort of convergent and divergent flow patterns that we saw in the damage from these crops. So a couple different things then, if you're interested. So here's just an example too. This is similar to what Letzman did way back in the 1920s, but basically a catalog of different patterns where you change your Gmax, you change your alpha, and you can basically see how the flow patterns change as you sort of change those parameters. And if you're interested, there's a software available, free for download on this page. This is called Design Safe in the US. So basically it sort of stores a lot of hazard data from various hazards, including wind. So it's published there. If you're interested in sort of downloading the software, taking a look at it, and testing it on things that you may see. I mentioned too, yeah, you'll have your homework will cover this. We'll sort of extend your Rankin model to include tree fall. Okay, questions? Thoughts? I want to see you guys do it on an Italian tornado at some point. Po Valley is the prime area, right? In Italy, Po Valley, along in the Po River, yeah, Po River Valley, yeah, yeah, okay, yeah. So it'd be interesting to see that extended. Obviously, that the sort of the concept started in Europe through some of the damages in the northern, like in Germany and some of the forests there after tornadoes come.
A couple of years back, there's strong tornadoes in Czech Republic.
Yes, yes.
I don't remember the classification, but it was quite substantial damage.
I think I seem to remember that, and I think too, yeah, things like obviously, tree fall patterns and things like that can easily be used on those tornadoes and I'm assuming at some point the IF scale will I don't know if they'll pick it up, but certainly could use it. And again, with aerial photos, sort of a lot more commonplace nowadays, you can get that information and be able to do some analysis on it.
Yeah.
Just by looking at which one was under in damage and which doesn't.
Okay. Yeah. So yeah, those are the interesting things that you can do. Yeah, with downburst too, right? So you could do a tree fall model with downburst just the same, right? All you're doing is you're switching out your wind field model, and that's it, right? So, and these things, like I said, they're super helpful. And also, we talked a little bit about yesterday. Without aerial photography, you may not even know that there was a tornado there, right? So we talked about some of the corn damage and things like that I showed from at the very first day. If you're on the ground, you probably don't even really notice it, or it's so far away from the street access that you don't see it. But the aerial photos can help identify some of these things. Okay. All right. Should we keep moving? Should we take a break? Keep going? A couple of the professors were teasing me that it's going to like 2.5 hours, 3 hours or too long. I said, I just have 1 week. It's not like, if it was every day for a semester, it would be 45 minutes, So we only have so much time to cover. There's so much good stuff. All right, well, we'll move on. And so what we'll talk about now, we'll talk about a little more formal but simple approach to wind damage modeling. Okay. Now, the framework that I'll present is generic enough to where it can be applied to any type of wind. Okay. But your homework will have to apply to 2 different types. Okay, and so we'll start. So how many of you have taken like structural reliability? Something like that, like a statistical, no reliability. Okay, so good. Maybe we'll learn. Okay, so there's a whole sort of subfield of what's called structural reliability. And it's really sort of very sort of probabilistic, statistical heavy methods of estimating things like the damage to structures. Okay, so the basic reliability problem, okay, looks something like this. Okay, so it's going to be easy conceptually to figure out. Okay, so here we're going to look at our probability density function. Okay. Okay, and we have 2 basically variables that we are interested in. Okay, one is we'll say L, which is the load. Okay, and then another probability distribution, okay, which we'll call R, okay, which is going to be our resistance. Okay, so if we're loading something, some structure, okay, some structural component, it has some resistance to the load. Okay, you also have some load from some potentially hazard or something like that. Okay, and so these are usually probability distributions. Okay, so they're going to have a lot of times a mean resistance value, okay, and a mean load value. Okay, so obviously load and resistance are going to have the same units. Okay, so these are probability density functions of load, okay, again, which we're calling L, and resistance, okay, which we're calling R. Okay, so really reliability focuses a lot of times on things like the probability of failure. Okay, so we'll say failure, okay, or okay, we'll talk about a little bit limit state. Okay, so it's going to be some self-defined damage scenario, I guess. Okay, failure or limit state violation occurs when what? Exactly, right? So we'll write it slightly differently here. We'll say when the resistance minus the load, okay, is going to be less than or equal to 0. Okay, so this is usually a formulation used. So if the load is greater than the resistance, okay, this equation is going to be less than 0. Okay, what we want to know is how frequent or how likely is failure to occur. Okay. Okay, so the likelihood of occurrence of this is termed probability of failure. Okay, so we'll say P sub F. Okay, so we have some resistance, we have some load. If the load is greater than the resistance, okay, you get a failure. Okay, and so the problem, okay, is usually rewritten as something slightly different. So usually the problem is written as the probability that some function G, which is a function of the resistance and the load, is less than or equal to 0, where G and anything inside there is called the limit state function. Okay, and within this G, you'll have a lot of different random variables, okay, that describe for load and resistance. Okay, so a little bit more complex. Okay, and in simple terms, okay, the probability of failure is really just the probability that the resistance minus the load again is less than or equal to 0. And we think about okay, so we say that this limit state function G has random variables for loading and resistance. So for wind, what are some potential for wind load, right? Think about the things that are involved in the computation of wind load. What are some random variables in the load that may be? Yeah, pressure coefficient, right? For sure. Anything else? Yeah, the wind speed, right? For sure. Yeah, wind speed, velocity, yeah, can vary. Okay, and there's some other things too that we can think about that we'll cover today that might be a random variable in the computation of wind load. Okay, so those are two big ones: the wind velocity and the pressure coefficient. Okay, so let's do a simple example since I won't go too into the mathematical heavy stuff since there's not a lot of liability knowledge, and I don't think it's really needed. Okay, so let's do example. Let's assume, okay, that these probability distributions are for both load and resistance are normally distributed. Okay, and also, and I think we just sort of covered it, right? So why are they probability distributions in load and resistance? Why isn't it just a single value? So yeah, so why are the load and resistance modeled by probability distributions and not just a single value for both? We pretty much said, right? These things haven't, yeah, exactly. They have uncertainty, right? They have some uncertainty associated with them. We don't know, even for a given wind speed, we don't necessarily know what the load is going to be, right? Okay, so that's the key thing, really. These things have a lot of uncertainty. Okay, so let's say we have two normally distributed variables, load and resistance. We have some limit state function, which we'll keep simple now, which is just, again, the resistance minus the load. Okay, if G is less than 0, okay, we're going to say, okay, we're going to get a failure. Okay, and so what these this function G may look like is something like this. Okay. Also normally distributed. Okay. For most things, what would you expect the mean in zero is failure, right? So where would you expect zero to lie on this probability density function, you hope? If this is the mean G value, would you expect that to be positive or negative? Or what would you hope it to be? Exactly. So what would you expect the mean G value to be? Would you expect it to be on average higher than zero or lower than zero?
If G is smaller than zero, it's stable, then.
Yes. Yes, exactly. So here, you expect this to be positive, you expect zero to be somewhere over here, right? Okay, you hope for most structure you design that your sort of, and we'll talk about this, that your average resistance is going to be greater than your load. Okay, so here, less than zero, okay, this is going to be our failure region, right? So over there is failure, anything where this G is less than zero. Okay, a lot of times you'll assume normal or log normal because these have very nice properties. So if you assume that they're normal, you can also assume this, right? So the mean of G is just equal to the mean of the resistance minus the mean of the load. And then the variance in G is then just the sum of the variances of the resistance and the load together. Okay, so these are just properties of the normal distribution. Okay, so that makes it easy to model. And so what happens now is, okay, you can then normalize this. Okay, and again, your probability of failure is what? It's basically integrating everything to the left of zero. Okay, and to do that, you can normalize and say the probability of failure is equal to this phi value, which is the standard normal CDF. Okay, back to our CDF discussion, is equal to 0 minus the mean of G over the standard deviation of G. Okay. Go back to basic statistics now. Does this look familiar to any of you? Some number minus the mean over the standard deviation. Exactly, right? It's like the, yeah. And so it's called like the Z, sometimes they call it like the Z score, right? And so here, this is in structural reliability, they call it something different. Okay, so I'll call this beta, but it's really sort of equivalent to a Z score. Okay. So again, you hope this to be negative, okay, because you hope that the mean of G is positive. Okay, and so this beta, okay, is called in structural engineering, okay, the reliability index. Okay. And so the larger the beta, okay, the safer the design. Okay, and for structures, okay, and I'm assuming they do it the same, they do it in ASCE, I assume they probably do it in Eurocodes as well. Okay, usually set a target beta for some limit state. Okay, and again, a limit state is really some defined damage state. So you could, like, going back to our EF scale discussion, you could set the threshold of damage as the limit state. You could set roof removal as the limit state. Okay, so some damage condition. Okay, so I'll show you an example. This one. Okay, so this is ASCE. So what you'll see is they'll have two things here. So really what I'm looking at is the bottom thing. We talked about the category 1 through 4 buildings briefly 2 days ago. Gives you an idea on top what that is. So it's really based on the number of people at risk in a particular structure. Okay, the bottom is these target reliabilities in ASCE that correspond to each of these 4 risk categories. So you can see the top, the 4 columns are the 4 risk categories. Here on the left-hand side is basically the defined limit states in ASCE for each risk category. So the limit states are broader: failure that is not sudden and doesn't lead to widespread damage progression, failure that's sudden and results in widespread progression or leads to, and then failure sudden that results in widespread progression of damage. And what you can see is they have 2 numbers there for each risk category. They have a probability of failure, okay, and then they have a beta value, okay. And so this beta value, which we said is our reliability index, is some target, okay, that's related to this annual probability of failure in this case, okay. And you can see that this beta value, as the risk category goes up, the beta value also goes up, which is essentially equivalent to, okay, pushing this 0 value further and further to the left, right? So if a 0 wasn't here, let's say 0 was out here, okay, and then this was the probability of failure, okay, that beta value is going to be higher, okay? Your z-score is going to be higher. Okay. Questions on that? Okay, so that's just a basic framework. There's, like I said, there's those 4 courses on structural reliability, if you're interested. Okay, so now we're going to take that concept, okay, and we're going to use that to model damage. Okay, so modeling wind damage, I probably said the same thing above. Okay. Okay, and how we're going to do that, and maybe Amal went through this when she did her class, is the development of some fragility function. Okay, and so now we're going to say the probability of failure given a particular wind speed. Okay, so this is kind of what we want to know. So we want to know what's the likelihood of failure if we have some specific wind speed. Okay, you can do it different ways too. Or you might see it written, okay, capital F, okay, we'll have lowercase f for failure, okay, as a function of some wind speed. Okay, and this is generally what's called a fragility function. Okay, so it's going to relate some hazard, in our case wind, okay, to some probability of failure or probability of damage. Okay, so this here too, okay, written like this is a conditional probability. Okay, the probability of something occurring conditional on the wind speed being a certain value in this case. Okay, commonly fragility functions are modeled as a log normal distribution. Okay, and a couple different reasons. One is that the resistance log normal is a positive function distribution. Okay, can't have negative. I mean, you can't have negative load, but not in the sense that you think, right? You can't have negative resistance. Okay, so everything's positive here. Okay, fragility functions written like this. Okay, capital F of V. Okay, you guys should recognize this as a CDF. Okay, and it's modeled like this. So phi again, so this is the standard normal distribution. Okay. Here inside is the natural log of wind speed minus the mean resistance over the standard deviation of resistance. Okay. Now here V equals wind speed, but in the problem, when you're developing these fragility functions, okay, that V is transformed into loading for the calculation, right? You'll basically have a wind speed, you'll transform that into load using things like pressure coefficient, everything else you guys know, how to compute the load, okay? And then you'll say, okay, for this wind speed, this is the probability of failure. And so really what the fragility function does is gives you the probability that the resistance is going to be less than or equal to R load. Okay, so as that wind speed gets higher and higher, okay, that probability is going to get higher and higher. Okay, so a couple things on this. So again, this is the standard normal distribution. Okay. Mu R here is the log median of resistance. And then standard deviation is the log standard deviation of resistance. Okay, so I'll show you a simple example, and we're going to do this, especially for those of you guys who are doing the homeworks, we'll do it. Okay, is just a simple example of a fragility function, right? It's just very generic, where wind speed is on your x-axis, and then the probability of damage is on your y-axis, okay? So here's your function. Obviously, intuitively, as the wind speed goes up, okay, we know that the probability of damage to anything, any limit state that we decide, will also increase, okay? And so generally, this is modeled with the log normal distribution. Okay, so question though, for you guys, is how okay, let's say I want to find this probability. Oops. Say I want to find this probability of failure given some wind speed, which is just what we showed on the fragility curve. Okay. Okay, what are some potential ways to do it? Yeah, exactly. Okay, so yeah, we know, or we can develop possibly statistics for the load and resistance. Okay, so we can do something like Monte Carlo simulation. So how many of you, I'm assuming that Edkis and Andy have done Monte Carlo a lot of times, right?
Yes.
Yeah, okay. So PhD students and postdocs, pretty typical, especially in wind, to do some sort of Monte Carlo simulation, okay? We won't go into too much detail there, but it's basically a random sampling from a probability distribution. Okay, you have a probability distribution, some known probability distribution, hopefully, that has some mean and standard deviation value, or you know the parameters of the distribution. Okay, you can randomly sample from that distribution. Okay. For example, I'll give you an example in MATLAB. Okay, an example, a lot of times in MATLAB, the function looks like this. It'll have some distribution identifier, GEV, okay, which is generalized extreme value, RND, which means you're going to sample, okay, randomly sample from that distribution, and then you would sort of list your parameters, okay? In the GEV, we mentioned that it has 3 parameters. You give them those parameters. You also then give the length of data that you want to sample. And so then you basically randomly sample from that probability distribution, okay? And you would get different values. So if you did it for, let's say, if you randomly sampled your Gumbel distribution fit from the homework that you had, it had some A parameter, it had some U parameter, okay? And if you sampled 50, if you randomly sampled 50 values from that distribution, it would be essentially a sample of 50 years of data from that distribution, okay? And you can use these techniques for a lot of different things. One being to test how valid your sort of distribution fit is. But yeah, so we won't go into detail. Some classes I'll teach, I'll go into a little more detail about how Monte Carlo simulation actually works, okay? For here, we just need to know that, okay, this is randomly sampling from a probability distribution. Okay, so let's give you guys an example. And I brought this over here thinking that it would make a lot more sense. Again, this is sort of a US centric example, Canada as well. Okay, so let's say what's going to do a wind damage simulation problem. Okay, so let's say first we have our statistics on resistance. Okay, and we're going to focus on a roof panel. Okay, so like a wood panel on a roof of a residence. Okay, resistance statistics. Okay, I'll show you a figure in a second. Okay, from the slides, this is going to be important for your homework. Okay, what you'll see are resistances of 2 nail types. Okay, so these are driven into the wood panel and connected to the roof truss. Okay, you'll see nails named 8D and 6D. Okay, 8D is a larger, longer nail. Okay, so you'll see it has more resistance. Also, okay, you'll see in this table of statistics, you'll see things like spacing. Okay, here it's 6/12 inches, and I'll show you what that means. Okay, we're going to focus on, so let's say we have this, we're looking at this roof from the top. Okay. This is a gable roof. Okay, so gable roof, if you look at it head on, maybe looks something like this. Okay. From the top, this is the ridge line of the roof. Okay, and we're going to look at basically a panel, a roof panel that sits on the ridge. Okay, it looks something like this. And again, apologize here. I'm going to use, this is 4 feet by 8 feet in dimension. Okay, and this 6/12 spacing means that, and basically the trusses generally are like every 2 feet here. Okay, so here's a truss. So this spacing is 2 feet. And then you're going to have nail spacing, okay, 6 inches on the edge, and then 12 inches away from the edge. Okay, so here this is 12 inches. Okay, so that's this is the edge spacing. And then this is the interior spacing. Okay, so this is the roof panel. The one that's shaded there is going to be the one that we're going to focus on. Okay, so we have resistance of the roof panel to loading. Okay, another thing that we're going to include is the dead load statistics. Okay, now I'm going to start using metric again. Okay, the mean dead load of these panels is 0.168 kilonewton per meter squared. And then the coefficient of variation, which I'll call COV, is equal to 0.1. Now, does anybody know what the coefficient of variation is? Yeah, standard deviation over the mean value, right? So it's basically in wind engineering, when we're talking about wind, it's the turbulence intensity, okay? Here, it's sort of the standard deviation of the resistance over the mean, okay? So it gives you just a ratio. Here, that's ratio is 10%, okay? So some variability. It really gives you a measure of the variability around the mean. Okay, so we have the resistance and we have the dead load, okay? Now we're going to have the wind load. Okay, we're basically going to say that the wind load, we'll call W, is equal to Q, which is our dynamic pressure. Okay, we all did this yesterday, GCP minus GCPI. In short, okay, and then Q, back in metric again, 0.613. Okay, this is going to be slightly different. This is an old version of ASCE, but it really wouldn't change the results. 0.613 KZ, KZT, KD times V squared. Okay. And so what I'll include, and I'll show the figures here. Okay, the stats are non-tornado. Okay. So let me show now the table in the slides, and I'll make sure that you guys are going to need these slides for the homework. So I'll make sure I try to get them to you today. Okay, a couple things. Here's an example of a roof panel. Okay, you can kind of see it here. This is kind of an example of a typical roof installation. Okay, the panel, even though it's kind of a blown up view, the panel is like here. Okay. So this is like a panel. Okay, it's nailed, and you can kind of see in this image, okay, nailed to the truss. Okay, and those spacing is to determine whether it's on the edge or whether it's on the interior of the wall. Okay, so that's how it's nailed down. And so this is going to be the focus of our work. Okay, so this is our roof panel. Okay, a couple things. Statistics. Okay, we'll show these tables. Okay, here's an example of why I listed things like the nail size, 8D and 60. Okay, what you can see is information on the size of the panel, the nail type, and then what you see is the resistance statistics on the far right-hand side. Okay, so for example, an 8D nail, 6/12 spacing, has a mean resistance of 57.7 PSF or 2.76 kilonewtons per meter squared, and it has some coefficient of variation associated with it. Also, it tells you what the distribution is in these tables. Okay, and this is from Lee and Rosowski 2002, I believe, which they did for hurricane, but we're going to transform some of these into tornado fragilities as well. Okay, so here's the resistance. I give you the dead load. Here are some of the statistics for the wind load. Okay, and I think there's a lot of room for improvement here. So in the ASCE context, okay, in addition to V squared and CP, which I'll show CP in a second, we have things like KZ, KD, there's the pressure coefficients there, okay, GCPI and GCP. Okay, you can see there's uncertainties for these parameters as well, right? So for various heights, various exposures, that KZ is going to change. We know that, right? We looked at those KZ profiles, height and exposure variant. KD has some uncertainty, GCP, and then, which I'll show on the next slide, GCPI is in there as well. Okay. And then the second one, as you guys know, that pressure coefficient, okay, is obviously going to vary dependent on the position on the building, right? So that CP is higher in the roof corners, for example, roof edges. Okay, it's less, it's, less negative on the roof now we're considering, okay, for different locations. And so here in this study, they gave for a roof slope, single roof slope, 18.4 degrees, values of the mean and the COV for the pressure coefficient. Okay. Now, why haven't you seen wind speed on here at this point? Okay, because, well, really we're building a fragility function that is conditional on wind speed. So we're just going to step through a wind speed value, 20, 30 meters per second, calculate the load distribution using the uncertainty and the other parameters, okay, and then come up with our probability of failure. Okay. All right. So limit state. Okay. What is it going to be our limit state here? Okay. We're going to make it very simple. We're going to say our limit state okay, is the removal of the panel by uplift. Okay. Easy enough. Okay. That panel is going to get removed, pulled away from the building. Okay. What's our limit state function going to look like? Okay, let's look at our, let's say this is our roof system, right? Maybe something like this. We're looking at some panel on the edge, let's say here. Okay, so this is our gable roof. Okay, what's our limit state going to look like here? What do we got working in? What's our wind uplift going to look like? Which direction is our wind force going to go? Up, right? Normal to the surface, but up, right? Okay, so what's opposing then our wind load? Yes, all right, so the nails and what else? The resistance here, what was our last thing? The dead load, right? So our dead load also, okay, going to oppose our uplift. Okay, so limit state function is going to look something like this. And I'll write it slightly differently. We know that when we compute the load for the wind, it's going to be negative because of the negative pressure coefficient. Okay, so it's going to look something like this. So it's going to be R plus D, okay, which is our component acting opposing the uplift, okay, plus our wind load. Okay, here we're going to assume that our wind load is going to be negative. Okay. So now, like we said, we can do Monte Carlo simulation, right? We can basically say, we can look at the likelihood of all possible outcomes, right? So all of these things, resistance, dead load, wind load, are all random variables. Okay, so we can then simulate various values for those, okay, and see how likely it is that things are going to fail for a given wind speed. Okay, so here we can do Monte Carlo simulation. Right, so now, when I have the MATLAB code up, so let me unshare over here. Okay, so let me zoom in. Online, you'll probably be able to see it better. Okay, so I'll share this as part of your homework. Okay, it has a couple intermediate steps in there that maybe you could skip. So what I'm gonna do is, okay, we have our wind speed statistics. One thing that you'll see back in the slides is that it has an exposure. KZ varies with exposure. So at some point here, I convert the roughness link to an exposure value. Okay, so I'm going to do 10,000 simulations for a given wind speed. KZT, you'll see on the slides, is just one, and it's deterministic. There's no variation there. And so what I'll do, and I converted everything into metric, basically you just create sort of an array of wind speeds here from roughly 18 meters per second up to around 90. And so what I'm going to do is just go through each wind speed. Okay, and you just create this sort of failure counter, the wind speed here. Okay, and then you're just going to loop through things a bunch of times. So here is the KZ value. It varies based on terrain condition, B, C, or D. I think this one is C. And so what you see, and also, yeah, so exposure C, exposure B, and exposure D. And so in MATLAB, it's just NR and RND. So that's the normal random variable with a mean. And then the standard deviation is just the mean times the COV. Okay, and I'm just doing it I'm just simulating one sample from the distribution to start. You can do it you could easily do it differently. Okay, so depending on the exposure, you'll have a KZ value. You'll get a directionality factor, KD. Okay, and then you have your, okay, so these were the, some of the wind statistics. You have the resistance statistics, which is the dead load. So basically the weight of the panel that's holding it down, plus the resistance of the nail. Then you have some of the aerodynamics, which is GCP and GCPI. Okay, which are also given in the tables. And then you're going to calculate your wind load, which we talked about, which is 0.613 KZ, KZT, KD, V squared. And then convert to kilonewtons here, divided by 1,000. Then you calculate your wind load. Okay, and then your limit state function is this. Here's your wind load calculation. Your resistance and your dead load values are up here in your resistance statistic. Okay, so you're just simply going to go through, you're going to compute your limit state function, and then you're basically going to say, okay, if G is less than 0, which we talked about was our failure, okay, we're just going to count that as a single failure. And so we're going to do that 10,000 times for each wind speed. Okay, and then we're just going to simply take the probability of failure being the number of failures that we counted over the 10,000 simulation. And at the end of the day, what you're going to do is then plot the probability of failure for each wind speed that you loop through. Okay. So let's see if this thing should run, but you never know. Maybe. Okay. And so then what you get basically then is a fragility function, okay, that describes the wind speed and then the associated probability of failure. So in this particular example, which was for a nailed roof panel, okay, when the wind speed gets to about 60 meters per second, okay, it's almost a near certainty that you're going to get roof panel failure based on the fragilities that you used in this example. Okay. And then looks like the damage initiation starts around, somewhere in the range of 25 to 30 meters per second is when you start seeing a small proportion of times where you would see some sort of panel removal. Okay. And this is pretty typical in wind too, where you see basically between 30 and 50 meters per second is where all the interesting things happen. You see almost always you'll have sort of damage initiation within this particular range of speeds. Okay, so let me stop sharing that. And I'll share the fragility with you. What I'm going to have you do, well, is, okay, there'll be a homework on that. Okay, give an example. So here's an example of, and we showed this the other day, KZ, or the square root of KZ, from the radar data and the code for tornadoes, right? So what we just did in the fragility was basically using information on the non-tornadic curves, KZ, which look quite a bit different than tornadoes, okay? So in the homework, you'll maybe modify some of those parameters to account for tornadoes. And then you'll see how the fragility curves change, okay, under tornado loading as opposed to ABL loading. Okay, another way that we can do it is to build empirical fragilities. And essentially, Monte Carlo is sort of one way to do that. Okay, what if we go out and we're left with something like this, where you're talking catastrophic damage, okay, no roof panel removal, for example, okay, we assume maybe it happened, but we don't really know. Okay, and so what we can do using some of the information we talked about today is use the EF scale as your limit states, okay, for residential construction, for example. You have DODs associated with that. Then, and it's not tied together too well, okay, we did this for a tornado in Missouri, is based on tree fall, you can get a wind speed at each of those structure locations. So instead of taking an EF scale wind speed, like this one for DOD1, you take what the wind speed is estimated from tree fall, for example, which is independent of the EF scale, and then develop sort of empirical fragility curves based on the different levels of damage. Okay, and so here's DOD1. So this curve will tell you for DOD1, which is the threshold of visible damage, okay, the likelihood that given a certain wind speed that the DOD is going to be greater than or equal to that value. Okay, so if DOD1 is the damage threshold, again, about 50 meters per second, okay, almost all the residential structures are going to have at least some damage. Okay, you can read it sort of that way. Okay, we were going to get into it for the class, but I realized that we wouldn't have the time. Maybe if I do this class again, we'll do a little more of that, work. Okay, any questions on fragility curves? Okay, so it's just, again, there's a lot of ways to do it. There's, like an earthquake, there's just an overwhelming amount of literature on fragility curves for everything that you can imagine, different structures, components. Wind, it hasn't been done as much, especially for things like tornadoes. But any questions? Okay. All right. So, okay, one thing we haven't talked about, and we'll talk about a little bit today, is debris. Okay, we've sort of danced around the issue. We haven't talked about it a lot. We know it's going to be an issue, especially in tornadoes where there's just a ton. And here's an example again from, this was a EF5 tornado in Missouri, where just to give you the idea, the scale, the volume of debris that's left behind after these events. Okay, not only just a crazy task to clean it up, but also how it sort of impacts other structures downstream. Okay, if you can imagine a house that gets damaged, okay, like some of the damages we've seen today, where the debris then gets carried on and impacts downstream structures, and then you sort of get this cascade of damage due to debris. Okay, so okay, debris. Okay, major cause of damage and of death in windstorms, especially in tornadoes. Okay, if you look at sort of where fatalities and injuries come from, most of fatalities and injuries come from blunt force trauma. Okay, due to debris impacts in these storms. Okay, and again, this is a direct result of some sort of structural failure. Okay, whether it be component, whether it be the entire structure. Okay, just like we talked about, for example, our roof panel. Okay, if the roof panel fails and flies off, now you have a source of debris in the wind field. Okay, now the modeling of debris typically broken down into three generic types. Okay, one is called compact debris, rod debris, and plate debris. Okay. And if you look in any textbook, typically debris is not given like super detailed treatment, but what you'll see is something that looks like this. Okay. You have basically three types of debris: compact, sheet, and rod-like debris. Each of those, notice too that they have some characteristic length dimension or length scale associated with them. Okay. And so can you guys think of, just looking at those, okay, in reality, what may be some common debris types that may take on shapes similar to that? How about this one? The roof panel, right? Yeah, roof panel is a pretty good example of sheet-like debris. Okay. Compact debris can be things like gravel, dirt, anything like that typically would be considered a compact shape. A rod might be something like a roof truss or something like that, or a piece of wood, for example. Okay, so generally in the debris modeling, okay, concerned about two things. Okay, one is the threshold of flight. Okay, so what wind speed or what sort of condition will it require for debris to fly? Okay. So for compact debris, so typically they, like most other things, it gets non-dimensionalized. Okay, so this sort of characteristic length scale L, okay, is going to be equal to 1/2 rho A UF squared times CF over rho M times G. Okay, where UF is the wind speed, at which flight occurs. Okay, so for example, you guys, in just a previous example, okay, you could estimate the wind speed which flight occurs. You could say in your Monte Carlo simulation, 40 meters per second. Okay, we get debris, we get a failure. Okay, so that's our threshold speed for that particular case. And then you move on to the debris part of the model. Okay, and then rho m is the density of the object that you're considering. Okay, and then obviously rho a is the air density, and then CF is the force coefficient of your debris. Just write that down. Okay, for sheet-like debris, okay, you'll notice that the characteristic dimension on there was like the thickness. Okay, and this is going to proceed the exact same way as the previous example. And then for our rod debris, okay, it's going to be a little bit different now. We're talking about some diameter. Okay, so this is going to be 2 over pi rho a UF squared CF over rho m times G. Okay, so here's some examples for that threshold of flight. Now, some of the damage surveys revealed that not everything leaves as debris. It might fail, and it might just sort of fall off the structure and land on the ground. Okay, so not everything that fails necessarily is flying through the wind field as debris. Okay, some of it may just sort of fall off and lay next to the structure. So there's no trajectories. Which is the next part of this. A key thing for this too, in general, is that there is no real full-scale validation. Now, I will say, both for threshold of flight and trajectories, things like CFD can be super helpful for this kind of thing. Not only just sort of being able to track debris, but also to get realistic dimensions of the debris. So you can see, in general, debris has sort of grouped things into 3 categories, right? And we know that real debris, based on what we've seen, okay, potentially have different aerodynamic shapes than that. Okay. Okay, so the next thing is trajectories. So, okay, so when it starts to fly as debris, where does it go? What path does it take before it finally impacts the ground? Okay, the focus here has been on sheet-like objects. Okay, and in general, there's been sort of one critical non-dimensional parameter that's been used to estimate trajectories. Okay, and this is called the Tachikawa number. Okay, this is usually given by the variable K. Okay, and it really relates the aerodynamic properties to the gravitational properties of the debris. So it looks something like this. Rho A U squared times A over 2 times the mass times the gravity. Okay, so this is really the aerodynamic parameters. This is really the ones related to gravity. Here, area is the area of the sheet-like debris. Now you'll see this used a couple different places. So one is used in you'll see the equations of motion. Okay, so you'll see some non-dimensional parameters. You'll see the Tachikawa parameter in there sometimes. Also can be used in empirical results. Okay, to compare to observed trajectories. And again, both of these are to estimate the trajectory of the debris. Okay, so that's sort of generic debris modeling. Let's talk a little bit about debris modeling in tornadoes. Okay, and a key paper for that recently came out is, and I mentioned this paper when talking about tornado wind fields, is from Baker and Sterling in 2017. Okay, so this paper has basically a wind field model, pressure model, okay, and then uses the wind field model to estimate debris trajectories. Okay. So in this paper, in most studies on debris, only focus on, especially CFD and sort of analytical studies, only focus on compact debris. Anybody take a guess on why that's the case? Why has been most of the focus have been on compact debris? Exactly. So the shape is easier to model. Basically, your coefficients, force coefficients are the same no matter which orientation it's in, right? So a lot of them assume that the particles or debris is spherical, okay? Much easier to model then. So you think about something like a sheet or a plate, right? If you just throw it like this 100 times, it's going to go somewhere different because the orientation changes. It's hard to estimate. It's hard to model the changing both force and moment coefficients depending on how it's created. Okay, so for a sphere, you don't have to worry about that. So most of these consider compact debris. And in this particular tornado, they did derive a two-cell vortex, but the debris has been focused with a single cell vortex. Okay, and they basically said there are three parameters, non-dimensional parameters of importance that tend to govern the trajectory of debris. Okay, the first one, which we mentioned yesterday a little bit, is the swirl ratio. Okay, and since this is not done in the simulator, this is just sort of a theoretical model. Okay, the swirl ratio here is defined as Vm over Um, where Vm is the max tangential speed and Um is the max radial speed. Okay, so that's something too where from even the Rankine model, okay, you can estimate what the estimated swirl ratio is. The second parameter that they developed was something they called a buoyancy parameter. Okay, and then this one was, again, so it's slightly different than the other debris models now because you're sort of relating, you're trying to come up with non-dimensional parameters that include parameters that are part of the tornado. So the buoyancy parameter is 1/2 rho A times Rm over M times CD. Okay, so here M is the mass of the debris. A is the debris area. Okay, and then Rm, again, should be familiar to us also, is the radius of maximum wind. And again, for spherical debris or compact debris, okay, CD then is, it doesn't matter how it's flying through the air, okay, that's a constant value. And then the last thing that they came up with, this third parameter, which is like, I guess that's psi maybe. Okay. Is equal to G times Rm over this lowercase um squared. Okay, they called this the inverse tornado Froude number. They were, again, Rm is the radius of maximum wind, G is gravity, and U lowercase um is the maximum radial debris velocity. And so they have, if you go to that paper, there's quite a few examples in there. I'll show one from the study here. Okay, with this buoyancy parameter, I think is equal to 10 in this case, this non-dimensional parameter that I mentioned. Okay, this shows sort of two views of the debris. So on the left-hand side, this is, and I don't remember exactly how they initiated the debris, right? You could model that too. But this sort of tracks it in height and radial space on the left-hand side. So here, I must have it start here. Okay, and it sort of goes around, comes back, and then it hits the ground at this point. Okay, so you can follow it through space. And then here's the plan view from the top down. So you can see here that it gets generated probably close to the tornado and then sort of spirals its way out, centrifuged out from the center of the tornado and ends up then close to back where it started. But this kind of gives you an idea of a particular trajectory that you can develop from these models, right? So, and again, the difference here is it's a tornado wind field model. The other ones assume that, again, the speed doesn't vary over some considerable distance, for example, and the direction doesn't either. Okay. Any questions on that? All right. I think we'll quit for today. Okay, what we'll do, we'll talk about, I'm exhausted, I don't know about you guys, but we'll quit for the day. We'll talk a little bit about codification tomorrow for the first hour or so, and then we're going to do presentations the rest of the time. Andy and Joseph in here are going to do them. We have Federico's going to do one, and then I don't have my sheet with me, but then I think 2 other people remotely will also do them. So we'll have at least 5 presentations tomorrow that discuss sort of latest research topics in this area. Okay. Any questions online? Okay, have a good night. I'm gonna upload the homework. I'll send that to you, and you can do a question from Alessia. Okay, she asked that in the Rankine vortex, turbulence is not considered, but it can affect and change aerodynamics of the building and consequently the loads. Yes, so that's a great question. In what you could do, in theory, is use boundary layer prescriptions of turbulence to add on to the Rankine vortex. Now, is that the right thing to do? I don't know. What I will say is that from some of the data that we collected in dust devils and the tornado, it seems clear that yes, if you did some sort of time averaging or spatial averaging, you would get a Rankine vortex, but there is sort of turbulence that's appended on. What the content of that is, I'm not sure. Another thing that you may need to consider are things like subvortices and things which aren't necessarily boundary layer turbulence. They're sort of tornado related turbulence that you may need to account for as well. So yeah, I think it's an open question, but there are sort of ways that you could do it. I think the first step would be to take some real data and fit a Rankine vortex and then sort of take out the residual turbulence and see what that content looks like. In sort of another sort of wide-ranging view, or some view people take, is that the vortex itself is a gust, and so you sort of treat it like you would just a normal gust, turbulence wise, right? Sort of isolate it and look at it independently. But yeah, an open question, but a good one. Any other questions? Okay, awesome. Thank you. One more class left, and then we'll be done. And on the homework, I think I'm not gonna make you have it done by tomorrow. I would say by Monday morning, if you can turn it in, then we'll be good. Okay, thanks. Thanks, folks. We'll see you. Thanks, Joseph. Yep. Tomorrow, presentations. Yes. All right, guys. Thanks, Peter. See you.
Thank you.
Thank you. Thank you, guys. We'll see you.